All right, good afternoon, everyone. My name is Timothy Sigmund. We are the Mr. Robotopus Firefight Competition team. These are my team members, Vasela, Tarek, Richard, Henry, Reggie, and Adnan. All right, so we're going to go ahead and talk about the agenda, and then we'll keep moving on. Some things we're going to be talking about in this presentation is the competition. We'll describe that to you. We'll talk about the design process, the control unit, navigation, communication network, locomotion, flame detection and extinguishing unit, project management, as well as the final words. So let's go and talk a little bit about the competition. The competition has a problem. This little sucker, this candle, is going to be a live fire on the first floor of the engineering building. But do not fret. We have a solution. Nah, that's ridiculous, right? We're not going to send a tidal wave after it. Our real solution is this. It's a small, fast, compact robot. And we designed this robot for the competition. So let me tell you a little about the competition right now. This is the general guideline of the course. Your robot has to be able to go through the first floor of the engineering building, be able to navigate autonomously on its own to find the candle. However, there will be 3 decoy LED lights trying to deceive the candle to make you think that it's the real one. Your robot has 100 milliliters of water per run to extinguish the candle. You can only use water to extinguish the candle. And the competition are 2 phases. In the first phase, you get 3 runs for your robot to try and find the candle and extinguish it. In the second run, all 4 teams will be running in a very chaotic manner, trying to race to the candle to put it out first. The team that puts the candle out in the fastest time is the team that wins. Now, we designed our robot for this competition to be small, fast, compact, and fast, but we also wanted it to be electronically and digitally fast so that it can compute very quickly with sensor feedback, etc. So I'm going to pass it off to Henry, and he's going to show us a little bit about the block diagram and the major components of our robot that makes it work so well.
Thank you, Tim. Hi, everyone. My name is Henry Santorio, and I will be giving you guys a brief overview of our design process and how it all ties together. As Tim mentioned, we wanted a light and compact robot. This gives us 2 advantages. It allows us to better navigate through the course, as well as have a better power-to-weight ratio. Right. In addition, we wanted to design have design that's unified and very efficient with our communication system. So right behind me here is the block diagram, and I'll begin with the array of PIC 16, which controls 6 of our sensors. Those sensors will communicate with our Raspberry Pi. The Raspberry Pi will store that information and send a very simple command to our PIC 32. Now, the PIC 32 stores all of our basic function that will allow the robot to drive straight, turn left, or right. And in addition to our sensors, we have an infrared camera that will assist us to identify the flame. So I will introduce to you Reggie, and he will go over the control system with you.
Hi, everyone. I'm Reggie Sanchez, and as Henry introduced, we have a Raspberry Pi as part of our system. Now, it may seem a little bit like overkill to have such a powerful device as a microcontroller in our robot. However, due to the design requirements that we as a team decided, this microcontroller was best suited for our robot. Now, the Raspberry Pi will be in charge of 3 primary things. It will be in charge of course navigation, sensor monitoring, and image processing for flame detection. Now, in order to accomplish this, and not overload the Pi because all these individual responsibilities would require a lot of processing power, we decided to use multi-threading, which we divided into 3 separate threads, 1 for each of those major tasks. Now, by doing this, we were able to distribute each of these tasks into 1 of the 4 processing cores, thereby reducing the overall load that the processor may have otherwise been under. So, the way we go about course navigation is by setting up the logic as a very simple finite state machine. There's 3 primary stages to this. There's searching the hallway, searching the room, and an extinguishing phase. Now, we only transition between these stages through very distinct requirements. Whenever we detect a door within the course, we'll go ahead and move into our search room phase. That way we can see if there's been a flame or decoy planted in there. As we navigate through this room, we'll be looking for a possible light source. Now, given that a flame and these decoys are both emitting infrared light, we have to be able to determine whether this light source is an actual flame or just a decoy. And we do this by using the camera that was previously mentioned. Now, given that we do determine that we see a decoy, we obviously have to make sure that we don't extinguish it and move on continuing our search. If it does happen to be a flame, we then move into our extinguishing phase where we shoot water at the flame to go ahead and put it out, at which point our run would be done and the robot would idle. However, if there isn't a flame present in the room, we have to exit the room, enter back in the hallway, and continue our search until we find a flame, or if for some random reason there isn't an actual flame, we go ahead and go into our finishing phase where the robot would idle again. And now, given that the robot has to do all this autonomously, we have to have a pretty good sensor array to help the robot know where it is in the course and be able to detect the flame. And to go over this, I'll pass it off to Vasela.
Hello everybody, my name is Vasela and I was responsible for the sensor configuration. So we have made a decision to use 3 different kinds of sensors in order to achieve autonomous movement along the course. The first one is the ultrasonic sensor. We place it on the sides of our robot in order to use its capability of a very wide field of view to look for openings, such as door openings. On the graph here is our test data, which shows that pretty much we are receiving the data and we're measuring accurately. This right here is our reading. We did decided to use its PWM reading, and also we are able, it's kind of on the fast side, and we have reading every 50 milliseconds. Next one. The next sensor we have implemented is the infrared sensor. It has kind of a short range, but that's what we look for because we use this sensor for object avoidance. There's a particular reasons we use only 3 of them, and they're situated at the front and both sides of the front side as well. As you can see, is an analog sensor, and if you relate the test data to the specs, it's obvious that it responds well. And also, we noticed that this sensor particularly have reflection, and it's really sensitive to distance. So that's why we're utilizing this to measure only distances, pretty much half of its original range. For the reading of the sensor, we're gonna use our control system. And this right here is our most valuable asset. It's the lidar. We have decided on it because of its very, very unique capabilities. First of all, it covers 40 meters of range. This is plenty, and it's 120 feet distance. It's accurate as it can get. We have really good reading backs, and we're working on, like we're talking about, a centimeter of accuracy for a length such as 5 meters. Another valuable thing of this sensor is that it produces data, like data readings really fast, and it's really user friendly as well. We have utilized also PWM as an output reading, and it gives us 10 microseconds for 1 centimeter of reading, which means that for the maximum of it, which is 40 meters, we're gonna be using only a block time of 40 milliseconds. So this is going to give us the biggest advantage of knowing at a pretty good timing, and we're going to be able just to make sure at any given time where are we at the course. Next one. And here I just want to show you how relevant is the sensor scaling with the course of with the field of course. As you can see, we did provide it, and we take it into consideration that we're going to use not the whole range of any sensor, and you can just see that the later will give us an accurate positioning even at the longest and the furthest distance in the course. Being said that, and give you just a little overview and an idea how fast is every reading made, we have to utilize this furthermore. And how we achieve this, I'm gonna pass it to Tim, who's going to give a better understanding.
All right. So SPI, Serial Peripheral Interface. This is a communication technique that we decided to use with our system. And one of the things that this uses is it has one device acting as a master where it can communicate with one or several slave devices. In our particular case, we're using the Raspberry Pi as the master device and several PIC16s and one PIC32 as our slave devices. We decided to use this instead of UART for a few reasons. One of them with UART, the communication would have to go from the Pi to the PIC16, synchronize both clocks between both devices, and then they can start transmitting signals, and then it has to go to the next PIC, do the same thing, and the next, and the next, and the next. We realized if we did this technique, we would have to be able to synchronize every single device, and it would take several hundred milliseconds. However, using SPI, we're able to cut that time down by a lot, because what happens is we're running our system in parallel. Essentially, it's a network built into our robot. And we're able to use a variety of different PIC sensors, and the way that the SPI works with the master here is the slave select line will drop low. It'll tell the PICs, hey, I'm going to communicate with you. All the PICs get ready. And in this daisy chain configuration that we're using, it'll drop the line and all the data will shift from the top one to the next. And then as many times as we have sensors. So in our case, we have 6 sensors. The Pi will very quickly send 6 clock signals and it'll shift the data between each PIC all the way through until it's sent back to the master. Using this configuration, we're able to use the SPI to communicate with all of our sensors in only a few hundred microseconds compared to several hundred milliseconds. It's substantially faster, much more efficient for our system. Furthermore, we can also add or subtract sensors very easily since it's in a parallel configuration with little conflict with time, etc. Next, I'm going to go ahead and pass it back to Richard for the locomotion.
Thank you, Tim. Hi guys, my name is Richard, and I was responsible for the locomotion and chassis design of the robot. So as you see, we chose a motor with 9.7 to 1 metal gearbox ratio. This is because this results in higher speeds. And we also chose these motors with motor encoders of 48 counters per revolution, just because, as you can see, is the right motor here is a lot 2% duty cycles faster than the left motor. And we're going to use these encoders to correct this error by using the encoder feedback loop shown on the next slide. Okay. Now the motor encoders measure the distance while the wheels turn using ticks. And we take these ticks of each motor, we'll compare them to each other, and then we're going to adjust the duty cycle accordingly, resulting in a straight moving robot. As you can see on the next slide, before the encoder feedback, it's very sloppy. It runs into the wall, it avoids me, I'm trying to pick it up. But after the encoder feedback, it goes straight, it's controlled, it comes back, no problem. Now I'm going to briefly talk about the chassis design and pass it along. So our goal is to get the chassis design to be compact and lightweight, which is why they designed this on SolidWorks at about 10 inches by 8 inches in size, and with a aluminum hardware for material for lightweight. Now I bet you are wondering why or how we're going to identify and put out the flame, which is why I'm going to give it to Reggie for talk about the vision system.
All right, everybody, so we've kind of teased that we're using a camera for this flame detection stuff that we're doing. And so given the fact that we are looking for a flame, it's going to be emitting some light. And so as you can see here, this is a decoy that also does a very good job of replicating that light source. However, in addition to our camera, we've also implemented an infrared filter, which helps eliminate all of this unnecessary visible light. And instead, we only pick up infrared light that's being emitted. This helps greatly with image processing because we don't have to worry about all of the excess images that would otherwise be in the background of our video feed. Additionally, we also then convert this video into a grayscale frame. That way, we don't have to worry about processing 3 separate channels of color, and instead reduce that overall workload to just a single 8-bit channel. And then to further help in the detection of the decoy and flame, we also implement some background subtraction, which would then result in an image that is purely black where only a white dot would appear on screen when we do detect a possible source of flame. And so to go over how we'll put it out upon detecting flame, I'll pass it to Adnan.
Hello, my name is Adnan Awazam. My part is to build the extinguisher unit. When the robot detects the flame, the robot will be placed in the front of the flame, and the robot will trigger, and the Raspberry Pi will trigger the MOSFET, and the MOSFET will turn on the water pump. As you see in this example, the water pump starts pushing the water. It will take less than a maximum 3 seconds to turn off the flame. The nozzle give us almost 7.4 milliliter a second, and we have 100 milliliter, which will give us many chances to turn off the fire. The range of the nozzle will give us up to 14 inch far from the robot, 12 inch by 4 inch diameter for the area that's being covered with water. So whenever the robot will be misplaced, like in 2 or 4 inch, an error will be the flame will be extinguished. And that's it with the specification for the robot. And next we'll move to the budget with Tariq.
Thank you, Adnan. Good afternoon, everybody. Today I'll be going over the cost analysis of our design. First of all, I would like to thank San Diego State University for providing us with a budget of $800. Our team has used this amount in the best and the most efficient way. Now, in order to have an autonomous robot that can drive and navigate through the course without hitting any obstacles, we specified the majority of our money to go on sensors and microcontrollers. As you see, they cost about 55% of our budget. Moreover, we spent the rest of the money on the locomotion units and the power of our system. With all that, we still have $20. As you see, we spent a total of $780. And now I'll pass it back to Tim to talk about our milestone.
All right, so we'll just go over our milestones real quickly. So we wanted to complete the chassis prototype. We were able to do that and accomplish it on schedule. We were also able to go over to the robot moving straight. We had some criteria here. We were a little delayed in that, but we were able to accomplish that task as well. We want to be able to get the Raspberry Pi and the PIC to communicate together. That was also accomplished. We want to be able to detect a potential flame from the knot, and we were able to accomplish that. To differentiate the flame from the decoy, it was a little delayed, as well as the flame detection with navigation. But we're working on that. And so now we are going to go and conclude. So thank you so much for listening to our presentation. We're excited to compete tomorrow, and we'd like to welcome all of you to check out our booth after the presentations are finished. Thank you so much.